If you don't already know, I belong to this amazing STEM program called the Knowledge Society, and during the month of November, innovators from TKS Toronto had the opportunity in teams to come up with a solution to improve customer service at Instacart. And my group decided to target the produce issue at Instacart since it's been known that sometimes shoppers deliver produce that is rotten. To put things simply, my group's solution was to create a live produce detection where someone would pick up their phone and scan a produce item, and our AI would determine whether it was fresh or rotten. And if the produce was fresh, the shopper could proceed to checkout, whereas if the produce was rotten, the shopper would have to keep scanning produce until our network deemed that it was fresh enough. So like you see in the photo here, someone scans produce, and then our network determines if it is rotten or fresh, and if it's fresh, we get a happy customer. Usually, in the food industry, hyperspectral imaging is used to carefully break down components of fruit. And essentially, hyperspectral imaging is a technique that analyzes a wide spectrum of light instead of just assigning primary colors to each pixel. The light striking each pixel is broken down into many different spectral bands in order to provide more info on what is imaged. And although my prototype that I created for this project did not make use of hyperspectral imaging, the goal was to focus on the computer vision aspect. So here are a few images in our training and testing data. So this particular neural network deals with 6 classes. So we have rotten oranges, rotten apples, rotten bananas, and we have fresh oranges, fresh apples, and fresh bananas. And there are a total of 5,501 training images and 1,384 testing images. And for this network, I used a convolutional neural network. If you don't already know what a convolutional neural network is, don't worry. I'll link a Medium article in the description below that walks you through the steps of one. And I wrote code for this prototype in both TensorFlow and PyTorch. So I will be including both versions so you can follow along in whatever library you'd like. I'll also leave my GitHub repository below for this code, as well as linking the Kaggle dataset that I used to train my network. Okay, so first let's start off with our imports. We're going to import TensorFlow as TF. From TensorFlow.keras.models, we're going to import sequential, which will allow us to add different layers to our neural network. And then from TensorFlow.keras.layers, we're going to import dense, flatten, conv2D, and max pooling 2D. And I'll explain how these layers work within our neural network later. And then from TensorFlow.keras.preprocessing.image, we're going to import image data generator. First, let's initiate what our directories will be for this neural network. We're going to have a train path that will store training data and a test path that will store our testing data. And we will also have a batch size variable, which will store a batch size, and we'll set it to 10. And essentially the batch size means how many samples are going to be fed into your neural network. I like to have a variable at the top for values that could be changed, because then that way you don't have to go looking through all of your code to find what you need to change. Instead, you just need to go to the top to refer to what you want to fix or alter. Now we're going to make our image data generators, and we'll have 2 of them. And essentially, we make these generators to perform augmentations on our batches of data. So first, we're going to use transfer learning, and we'll use the VGG16 model to familiarize our model. We're going to rescale the images to 1/255, and this essentially converts all the pixel values to 1 and 0. And then we're going to have a horizontal and vertical flip just to randomize our data, and this will help with training. And then we're going to call the flow from directory method, which will allow us to specify our path that we want the augmentations to be performed on. We'll reshape our images to have a target size of 20 by 20. We'll initialize our classes, which will be fresh apples, fresh bananas, fresh oranges, rotten apples, rotten bananas, and rotten oranges. We'll set our batch size to our batch size variable, which we created earlier. And then our class mode will be categorical, and our color mode will be RGB, which stands for red, green, blue. And then we have our test batches image data generator, and it'll look the same as the training batch one, except there is no vertical or horizontal flip because we don't really want to alter our testing data like that. And we're going to set the shuffle to false. We want our testing data to be like something the network has never seen because we want to evaluate how well it can perform on that data. And then we'll make our actual model. So we'll use sequential to allow us to add different layers to your model. Our first model will be a conv2d layer, which will have 32 filters, filter size of 3 by 3, use the ReLU activation, and we'll specify the input shape, which is 20 by 20 and then 3. And then we'll have a max pooling, and then we'll have our conv2d layer, another one that has 64 filters, the same filter size, and then we'll use the same activation, and we'll have another max pooling layer. And then we're going to flatten our input because we need to do this when we get to the dense layer, and we'll have 128 neurons, and we'll continue to use the same activation that we've used previously, and we'll have 2 of those layers. And then our last layer will have an output of 6 because we have 6 classes, and we'll use the softmax activation. Finally, we'll be able to compile our model, and we'll use Atom as our optimizer, and we'll use categorical cross entropy, and this is because we have multiple classes that an image can belong to, and we'll measure the metrics of accuracy. And for this particular project, I found that 17 epochs gives you the best result, and we'll fit this and evaluate using our test batches. I've actually pre-ran this model because it would have taken a bit of time, and I didn't want to waste that time waiting for the model to run. So as we can see, these are my epochs. I'll just scroll through them really quickly. You can look at them, and we can see that our 17th and last epoch gives us a pretty decent loss and an accuracy of around 98%, which is pretty great performance. Okay, I'm going to walk you through the same program, but in PyTorch. So first we're going to import Torch, and then from Torch Vision, we're going to import datasets, transforms, and utilis. We're also going to import torch.nn as nn, and we're going to import torch.optim as optim. We're also going to import OS, and we're going to import numpy as np, and we're going to need this later for when we work with data and we have to do things with it. And we'll also need it for other mathematical calculations. And we'll import matplotlib as plt, and we'll import torch.nn.functional as f. So firstly, we'll create our training and testing directories, as well as a directory that contains both the training and testing data. So we'll create a fruit train, a fruit test, and a data directory, which will have both of our fruit training and fruit testing data. Then we're going to use our transform to make transformations on our training and testing data. So we're going to use the transforms compose function on both the training and testing data. We'll resize the images to 224 by 224, and we'll do this for both the training and testing data. We'll perform a random horizontal flip on the training data, but not the testing data because we don't want to augment our testing data in that way. We're going to transform to tensor, and then we're going to normalize our data. And then here, we're just going to perform our data transformations on our training and testing directories. And we've made a data loader right here. And we'll essentially make distinctions of what we want to happen in our data loader. So we'll set the shuffle to false when we're doing testing because we don't want to shuffle our testing data, and I'm running this on our test data. We'll set a batch size of 124, so these are the amount of images that'll be propagated through our network, and we'll perform these for training and testing data. And then right here, I've just written some code to do some visualization. I like to see what data I'm working with, and it is this image right here. And it just gives you a little bit of a look of what we're doing and what we're working with. Now to the actual model, we're going to inherit from the nn.module, and we're going to have our first convolutional network that will take in 3, 16, and then we'll have a kernel size of 3 and a padding of 1. And then our second network will take in the 16 and 8, and we'll have a kernel size of 3 and a padding of 1. And then we'll have a linear layer, and we'll have a second linear layer, and then we'll use the ReLU activation. And then for our forward function, we're going to perform max pooling twice, and then we're going to flatten our data before we get to the dense layers because we have to do that. And then there's the ReLU activation again, and then we're going to return our value. Okay, and then we're going to make an instance of our class. We'll use Atom as our optimizer, and we'll have a learning rate of 0.0001, and we'll use cross entropy for our loss. And I'll perform this in 20 epochs. So we'll perform our training data stuff, and we'll train the network in this loop. And then we're going to perform our evaluation with the testing data, and we won't use gradient because you don't want to use that on your testing data. And I actually pre-ran this because it does take a little bit of time to run on your model. I'm running this on PyCharm. If you were to run this on your GPU, it would be faster, or something like Google Colab, but I'm running this on PyCharm in my CPU, so it takes a bit of time. So I just wanted to run it to make it faster, and we had a decent accuracy of 92%, which is pretty good.